America, Sean, Anthony, Zoe. Good morning. Are you the first one to notice that question? Let's see. Perfect. Good morning. Let's see. Are you Logan? Yes. Perfect. Good job. Well, it's 9 o'clock, so let's go ahead and get started. So I got to ask you a question. Are any of you 10,010 years old? Good morning. Are you Ignacio? Arturo. Oh, I apologize. Arturo. I'm sorry. I knew that. Okay, let's see. I just had the other person's name on my mind. Are any of you 10,010 years old? So when I first asked the question, I didn't specify the details. I just wrote 10,010 like that. But then as a hint, I wrote that next to it. Sorry, it's not coming out very quickly. I wrote the 2 next to it. So when we say somebody is a certain number of years old, we actually are a little bit ambiguous of what we mean. Because we are assuming that they know what number system that we're using, right? So the number system that we use in the United States and in a lot of the world is called the base 10 number system, right? The base 10 number system. So if you study number systems around the world, you'll find a lot of different strange number systems. For example, the Egyptians used to use a number system that looked like a stack of plates. So like the first plate held like 5 things on it. The next one was bigger and it could hold more things. And so then you had like a stack of up to 5 of them. And then you had like a bigger stack above or whatever that like represented more. So it's actually very similar. We don't think about it that way. But the base 10 number system is basically like, let's say if you are 18 years old, that basically means that you have 8 ones, right? So you have like 8 small plates, plus you have 1 extra 10-inch size plate, like one big plate that holds 10 times as much as the small plate, right? So 18 basically means you have 8 ones plus 1 10. Does that make sense? So what number system do computers use though, by the way? So people around us usually use the base 10 number system normally. But like I said, some countries use other number systems that might represent other things like that. So what number system do computers use currently, at least? Now, some people have tried to make computers that used other systems of numbers, but currently computers use the base binary system, which is the base 2 number system. And that's because they use transistors and diodes and things like that in computers that can have 2 states, an on or an off. So it's just natural for them to think of things as either a 1 or a 0. So this 2 right here is used to make it not ambiguous, but perfectly clear which number system is being used. So are you 10,010 years old or more? Let's find out. So if computers use the base 2 number system, then the 10,010 is written in base 2. That means this is the ones place. You have 0, 1s. Sorry, that looks like a clock for some reason. You have 0, 1s, plus this is the 2's place. So you have 1, 2, and then that's now every time in the binary system, it means doubling. So what you double the 2, what's 2 times 2? 4. So you have 0 4s in the 4's place. And then you double the 4, that'd be an 8. So you have 0 in the 8's place. Then you have 1 and double 8, what do you get? Yes, you have 1 in the 16's place. So what age does that represent? 10,010. If you have one value that's worth 2 years and one value that's worth 16 years, what's the total of 2 plus 16? 18. So actually, if you're 18, you're actually 10,010 years old in base 2. Does that make you feel old? And if you're more than 18, you're even older than that. So computers use the base 2 number system. They use, and that there's actually some good reasons for that. So let's try doing an arithmetic problem. Let's try that real quick. So let's just try, let's say 15 plus 18, let's say. So let's do it in base 10. So this is in base 10. So what's 15 plus 18 in base 10? How do you do it? This is gonna take you back to like 4th grade or something. So what's 5 plus 8? 13. Now you only have room for the ones place, so you put the 1 of the 13 at the top, 3 of the 13 goes below. And then in the 10th place, you have 1 plus 1 plus 1, which is 30. So 33, right? Which is how old Jesus was when he died. So you get 33. So 15 plus 18 is 33. Now let's convert 15 and 18 both into values that are in base 2. In base 2, you can only represent something by powers of 2. So now you can have a 1 in base 2 because 1 is 2 to the power of 0. So 15 is, how can you represent 15 using nothing but either 1 or powers of 2, like 1, 2, 4, 8, only things that are doubles of each other. Is there any way to represent 15 using only numbers that are doubles of each other, starting with 1? Well, that's actually, we learned last time, there's a word called mod. You remember what mod is? Mod means the remainder when you divide by something. So in order to figure out the first digit, we have to figure out what the number 15 is mod 2. So what is 15 mod 2? What's the remainder of 15 when you divide by 2? It'd be 1, right? So the first base 2 digit of it is 1. Now let's cancel that 1 out from 15 and get, and let's just leave you with 14. Now, how many times is 4? Well, actually, what is let me think. Actually, that's probably not a good way of doing it. Let's just get rid of the 1. So you have 1. Let's get rid of the 1 from 15 and leave it with 14. Now, how many times could you use a 2 to go into 14? 7, right? So let's see, what's the biggest power of 2 that can go into 14? Can 4 go into 14? Yep. How many times does 4 go into 14?
3 times.
3 times, right? Can 8 go into 14? Yep. Once. Can 16 go into 14? No. So let's actually, okay, so let me erase that actually. That's a little bit too complicated. We know 16 cannot go into 15, right? 16 cannot go into 15, so the biggest power of 2 that could go into it would be 8. And then after that, we could have a 4, and then after that, we could have a 2, and then after that, we could have a 1. So how many 8s are in are in 15? How many 8s are in 15? Just one, right? And so then after you take 1 8 out of 15, what is left? So 15 take away 8 would be what? 7. So how many 4s are in 7? 1. And then how many? So let's take 1 4 away from 7 and you get 3. So how many 2s are left in 3? So is this making more sense? So you start with 15, you get the biggest possible power of 2 that can go into it, which is 8. How many times does it go into it? 1. And then how many 4s are in, and then what's left after you take 8 out of 15 is 7. So then you go down and how many 4s are in 7? 1. How many 2s? And then you take 4 away from 7 and you get 3. How many 2s are in 3? 1. And then if you take 2 away from 3, you get, what's 3 minus 2? 1. How many 1s are in 1? 1. So 15 in base 2 represents 1 1. It's 1 1 plus 1 2 plus 1 4 plus 1 8. So therefore 15 in base 2 is equal to 1 1 1 1, like that. And then how about 18 in base 2? We already learned that 18 in base 2 is 10,010. That's 10,010. So let's add together 1111 plus 10,010 together. But we're doing it in base 2 though. And so that means you cannot actually ever use any digits except for binary, which is 0s and 1s. So what's 1 plus 0? That's it. That's easy because it's just 1. 1 plus 0 is just 1. What's 1 plus 1 though? It's 0, except it's bigger than 0, so it's actually, except you can't use 2 though. So you have to use 10. So 10 in base 2 really means 2. That's takes an extreme amount of brain warping to get used to that. But think about this though. 10 in base 10 means 10, right? So we think about 10 in base 10 meaning 10 because we're used to base 10. But the thing is, if you lived in a world where everything was in base 2, then 10, of course, would not mean what we think of 10 anymore, because their base system would represent 10 to mean 2. So basically, the number 10 in whatever world you're living in, 10 actually represents the base itself of the system. So when you get 1 plus 1 is 2, in base 2, you do not say 2, because 2 is not 2, it's actually 10. So 1 plus 1 is actually 10. They put out 10. Then you have 1 plus 1 plus 0, which is 2, but there's no 2. There's just 10. Then you have 1 plus 1 again, which is 10 again. 1 plus 1 again, which is 10 again. So you get 100,001 in base 2 when you add 15 plus 18. So any questions about that? Now, the question is that really the same as 33 or not? Who believes that 1001 is the same as 33? Okay, good job. And the reason it is because remember this, in base 2, this represents the 1's place. This represents the 2's place, the terrible 2's. This represents the fantastic 4's. And what's double of 4? 8. That's the 8's place. That's the 16's place. And that's the 32's place, right? So if you had 132 value plus a 1 value of 1, 32 plus 1 is 33, right? So 100,001 is the same as 33, actually, when you're talking about base 2. So base 2 uses very big looking numbers to do things with, but that's going to actually be a benefit for what we're working on in computer science. So let me go ahead and do attendance some more again. So let's see. Amani, good job. And let's see. Anthony, are you here? That's not. So let's see. Olivia Isaac. I don't see him. Noah Anthony Johnson. No. Colin Morrison. No. Ignacio. No. Caleb. No. Arturo. You are here. Yep. Okay. Mercade, you are here. Okay, good job. Okay. There we go. So let's go back to what we were talking about last time about modular arithmetic. So first of all, let's actually do one more practice problem in base 2. So somebody give me a number between 1 to 25. 13? Okay, I think we already did we already do 13? No, maybe not. We did 15. Okay, 13 is fine. It's a little bit easy, but that's all right. Okay, what's the biggest power of 2 that can go into 13? 8. You're right. So basically, this has 1 8 in 13. Now subtract 8 from 13, and what's left? 5, right? Yes, you're right. Now go down to the next lower power of 8. Of 2, I mean, sorry. So what's half of 8? 4. How many times does 4 go into 5? Once, right? So there's 1 4 in 5. So subtract 4 from 5, and you're left with 1. And what's the next lower power of what's half of 4? It's 2, right? So does 2 go into 1? No, it's 0 2s in 1. Now what's half of 2? 1. So there's 1 1 and 1. So then we start from the ones unit, which is the 1, and then the 2's digit, and then the 4's digit, and then the 8's digit. So 1101 in base 2 is equal to 13 in base 10. Does that make sense? Now notice that when you go by powers of 2, you can never have a power of 2 go, the biggest power of 2 go into something more than once. That's what's cool about powers of 2. So, like for example, the biggest power of 2 that can go into 13 is 8, and it can't go into 8 more than once. And 8 can't go to 13 more than once. Why not? Because if it could, then what would that imply? If 8 could go into 13 more than once, that would mean it could go into it at least twice, which means what? Which means that 16 could go into 13, and if 16 could go into 13, 16 is actually a bigger power of 2 than 8 is, right? So the biggest power of 2 can never go into a number more than once, or else if it could, then it would not be the biggest power of 2. So that's why in binary, things can never go into something more than once when you take the biggest power of 2 that can go into them. So that's the reason that there's only ones and zeros in base 2. Now let's talk about one of the coolest things in all of math. It's really, really amazing. So what if you wanted to compute the remainder, so of a, like, let's just say of 2500 mod, let's just say let me think. Somebody give me a number between 0 to 20. 18. So what if you wanted to calculate the remainder of 2500 when divided by 18? That's going to be pretty difficult, right? You'd have to divide 18 into a lot of different numbers. So here's the coolest theorem maybe of all. It says this. It says that A times B mod M is equal to A mod M times B mod M. That's the secret basically to how encryption works and everything else in modular arithmetic with computers. So hold on just a second. All right. So let me just make sure the sound is working again, because one time when somebody called me, I think it disconnected the audio and the whole thing didn't have any. Hello? Okay, good. The whole thing didn't have any audio. Okay, perfect. See, those silly junk phone callers don't realize that they might mess up an entire class recording. Okay, there we go. So what does that mean exactly? What does it mean if you say A B mod M is equal to A mod M times B mod M? Well, here's an example, 2500 mod 18. Can I apply that theorem to 2500 mod 18? Well, 2500 is literally 25 times 100, right? So 2500 mod 18 is equal to, that's equal to 25 times 100 mod 18. Do you agree with that? And who can tell me what 25 mod 18 is? So this is equal to 25, according to that theorem, it's 25 mod 18 times 100 mod 18. And who can tell me what 25 mod 18 is? What is 25 mod 18? What's the remainder of 25 when you divide it by 18? Or what's left over from 25 after you subtract 18? 7, yes. So this is 7. And then now you can do this in your head if you want to, but you could actually reduce it down even further, because 100 also can be factored into 25 times something. 100 can be broken apart into 25 times what? 25 times 4, right? So it can be broken, 100 mod 18 can be broken apart into 25 mod 18 times 4 mod 18. So then you'll get 7. And what's 25 mod 18? We just did it before. 7, right? 7 times 7 times, but what's 4 mod 18? Actually, I made one small mistake in that theorem. So AB mod M is equal to A mod M, B mod M, but then you still have to simplify the remainder of mod M as well. So let me add one more mod M to the end of that sentence. See right there, that sentence right there? So AB mod M is equal to A mod M, B mod M, and then still keep on doing mod M at the end. So 7 times 7, and then 4 mod 18 is 4. But then you actually have to keep on doing it mod 18 at the end. So I need to add one more mod 18 at the end of each of these. Why is that? Why do you keep having to add mod 18 to the end? The reason why is because, as you see, when you take 4 times 7 times 7, that's going to be bigger than 18. So of course you still have to reduce the remainder to be mod 18 at the end. So what's 7 times 7 times 4? Which one do you want me to do first? The 7 times the 7 or the 7 times the 4? Let's do the smaller one first. What's 7 times 4? 28. So you got 7 times 28 and mod 18, right? And according to that theorem, we can reduce 7 times 28 mod 18 by doing mod of 28. So basically, the moral of the story is anytime you're multiplying things together, you can reduce any factor in a multiplication by the remainder of it when you're trying to find the remainder of the whole thing. So on your way to finding the remainder of the entire problem, you can actually go ahead and find the remainder of any factor within the problem as well. So what's the remainder of 28 when you divide by 18? Wouldn't it be 10, right? Yep, it'd be 10. So that'd be 7 times 10 mod 18. Perfect. And what's 7 times 10? Well, that'd be 70, which would still be kind of big. So what if I factor the 10 apart a little bit? So 10 can factor into, was that even worth doing? Well, 70 is not too big. So 7 times 10 is 70. What's the remainder of 70 after you divide by 18? Let me think. 18 times 2 is 36. 18 times 3 is 54. what's the remainder after you take 70 minus 54? What's 70 take away 54? I believe it'd be 16. So that's cool. Hold on just 1 second. I'm gonna do something. Interesting. Wow. That's disappointing. Okay. So we get 16, so that's pretty cool. Now, does this actually tell us how many times 18 actually goes into 2500? No, it doesn't. So you can actually calculate what the mod of something is without even, hold on just a second, this is taking a long time to clear. You can tell how many times something goes, what the remainder is without even knowing how many times 16 goes into 18. So 18 actually goes into 2500 138 times with the remainder of 16. But yeah, but we never actually had to figure out the 138 in order to calculate the answer. So that's one of the mysteries of math. How do you know what the remainder is when you don't even know how many times the number even goes into 2500? So let's go ahead and figure out what application could you use for this. So this is going to be a little bit surprising of an application. So I'll have to go kind of slowly. But if you look at these sections of math, you'll see at some point, I don't think I printed out that far actually, but at some point you'll find out that one of the goals of discrete mathematics is to try to reduce very large powers of numbers. Very large powers of numbers, mod m, mod some other number. So modulo some other number. I'm just going to say some other number. Now this is going to be really, really strange because this is going to tie together powers of 2 along with the shortcut that we just learned. So are you ready for the mystical, magical way of doing it? So I have an example here. I'm afraid it's going to be a little bit beyond your heads though, but let's just go ahead and try it. I tried doing one as small as possible. The book has some examples that are a lot bigger, which definitely are way too big to understand. Let's try to do 13 to the power of 35 mod 7. 13 to the power of 35 mod 7. Now, why can you not do this the normal way? I'm just going to try this on my calculator. 13 to the power of 35. Okay, so if you do this on your calculator, it says 9.72. It has like so many digits and then 38 powers of 10 at the end. So you get a decimal point. This is not the perfectly accurate answer because it has rounded off to decimal places. So even that small number, 13 to the power of 35 mod 7, is too big for the calculator to compute accurately. So how do you do it? Well, you have to use some sort of computer program to program it to do it. And it actually can be done in only just a few tiny little calculations if you use base 2 to represent the 35, and if you use the shortcuts that we've talked about to represent the 13 to the power of 35. So let me work through this thing with you real quick. So the first step is to break the 35 down into the biggest possible power of 2 that it could be. So what's the biggest power of 2 that can go into 35? So 8 is a power of 2, right? How about 16? 8 times 2 is 16. And then how about 32? What's 16 times 2? 32 goes into it, right? So 35 is basically equal to 32, which is a power of 2, plus how much is left over after you take 32 out of 35? 3. What's the biggest power of 2 that goes into 3? 2 itself, right? So it's equal to 32 plus 2 plus, and then so 35 is 32 plus 2, which is 34. How much is left? 1, right? Now remember, we have to think of what power 32 actually is. 32 is actually equal to, is it the second, third, fourth, or fifth power of 2? It's the fifth one, I think. And 2, of course, is 2 to the power of 1, and 1 is 2 to the power of 0, right? The first step is to take the 35, the power, express it as a series of base 2s, like that. So we got 2 to the fifth times 2 to the first times 2 to the 0th, plus 2 to the 0th. Now, do you remember this? Do you remember this from college algebra? Do you remember that if you have a to the power of like 3 plus 5, that's what you get if you multiply together a to the third times a to the fifth. Remember, a to the third times a to the fifth is equal to a to the 3 plus 5. Remember that? So if you take a to the power of 3 times a to the power of 5, you add them together and you get a to the power of 8, right? A to the power of 8. So we're actually going to use this property right here. A to the power of 3 times a to the power of 5 is equal to a to the power of 8. And that means that I can take the number and also work it backwards like that. So I can take the number a to the 13 to the 35 power and break apart the 35 and say 13 to the power of 35 is equal to 13 to the power of 32 plus 2 plus 1. Do you agree with that? 13 to the power of 35 is equal to 13 to the 32 plus 2 plus 1 power, because that's just a different way of writing 35. And that's equal to 13 to the power of 32 times 13 to the power of 2 times 13 to the power of 1. And who would agree with that? Do you agree with that? And now I'm going to write each of those things as powers of 2. So that's equal to 13 to the power of 2. Now, what is 2 times 2? That's 4, right? And then what's 4 times 2? That'd be 8. How many more of the things do I need to add? 13 to the power of 32 is equal to 13 to the 2 squared. 2 times 2 is 4 times 2 is 8. Well, there's going to be a lot. There's going to be 5 of them, right? The 13 squared, that makes 4. Squared makes 8. Squared makes 16. Squared makes 32, right? So there's a reason for this, though, because we're expressing everything as a power of 2. Now that we've expressed 13 to the 35 as all those different powers of 2, now we're going to just reduce it mod 7. So what's 13 to the 35 mod 7? It would equal that mod 7, which would equal that mod 7, which would equal this mod 7. And according to that theorem, I can reduce each factor that's within it by the remainder mod 7. So what's 13 mod 7? What is 13 mod 7? What's the remainder of 13 when you divide it by 7? So it's 6. Yep, correct. So you get 6 to the power of 1. And then what's 13 squared? Actually, we don't need the power of 1 because that's just going to be 6. What is 13 mod 7 in the other one? It's also 6, right? And what's 13 mod 7 in the other one? That's also 6. So we reduce those all to be 6s. Like that. So we get 6 squared. Now let's reduce the 6 squared. What is 6 squared? What is 6 squared? Close. What is 6 times 6? Yep, 36. And what is 36 mod 7? So 7 goes into 35, right? So 36 would be one more than that. So the remainder of 36 mod 7 would be 1, right? So we can reduce the 6 squared to be just 1, like that. And we can reduce that 6 squared to be 1. So then we get 1 squared squared, and there's only 4 squares left now. So we get 1 squared 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 times 1 times 6. And 1 squared 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 is still 1. So you get 1 times 6. What is 1 times 1 times 6? It's just 6, right? So we just get 6 for that. And it only works if you express the power first as powers of 2. Then if you explain it all as powers of 2, then you can figure out what the squared one is mod that. It reduces to something super small, like 1 or 2 or 3 or 4 or 5 or 6. Once you figure out what that is, then the whole problem breaks down exponentially fast. So this is called the, let's just see. I think they have some kind of a name of it. They call this the fast modular exponentiation algorithm, algorithm 5, on page 268. Of course, if you look at the algorithm, it's kind of hard to understand it, just reading what they say. Fast modular exponentiation algorithm. So that's pretty cool. And they use it on a huge example with like power of 644, and it's modulo 645. But even in that case, it only takes them like 9 different steps to get the answer. So let's just go ahead and do. Let's do a couple problems together. Going back to some more basic ones. Let's see. Somebody give me a number between, like, say, 1 to 4,000. Maybe actually between 1,000 to 4,000. $1,526. And somebody else give me a number between, let's say between 25 to 50. 27? 37? So let's try to figure out 1526 mod 37. And just to save time, we're going to, what we're going to try to do is to try to find the prime factors of 1526. So let's go to the internet. Prime factors of 1526. So that's actually a pretty tough example. So 1526 only has one prime factor. 1526 is equal to 2 times 763. Like that. So 1526 is 2 times 763. And so we have to figure out what 763 is mod 37. So there's not really a lot of shortcuts we can do because we're still left with a pretty big number. So 37 goes into, what number does 37 actually go into though? How about 370? Does 37 go into 370? So that means that we can go ahead and subtract 370 from 363. So if we cancel out 370 from 763, we'll get, let's just see, we'll get 7 63 minus 370. 763 minus 370 is 393. And what theorem are we using? We're using the theorem that says that you can reduce any factor of a number modulo whatever the remainder is. And then we can subtract another 370 from 393. So what's 393 minus 370? That'd be 23, right? So 393 minus 370 is 23. And then now we can go ahead and multiply 2 times 23 together. And that would be 46. And then what's 46 mod 37? Well, you can subtract any multiple of 37 from 46 to figure out the remainder. So, to make it closer to the remainder. So what's 46 minus 37? What's 46 minus 37? It'd be 9, right? So we're left with 9. Like that. So 1526 mod 37 is equal to 9. So somebody else give me a number between 1,000 to 2,000, or between 1,000 to 4,000. So somebody make up a number from 1,000 to 4,000. 1,500, smart. And somebody else make up a number between 25 to 50. 29. So let's see if we can reduce 1,500 mod 29. One way to do it is to keep subtracting multiples of 29 from 1,500, like 290, right? 29 times 10 is 290. So we could subtract 290 a lot of times from 1,500. But we could also factor 1,500 into a number. So what are the factors of 1,500? Well, it's 15 times 100, right? So that one factors a lot more nicely than before. Can 100 break down at all any further? Or can 15 break down any further? Yeah, they both actually can. So 15 is actually 3 times 5. And 100 is actually 25 times 4. Yep, 25 times 4. And let's see. 25 times 4, and then 25 is equal to, what is 25 equal to? 5 times 5, and 4 is equal to 2 times 2. Why would you want to break it down so small? The reason you might want to break it down so small is because that gives you some options for coming up with a number whose value is close to 29. So it's easy to find the remainder, mod 29. So what's a number close to 29 that we could maybe get out of 5 and 5 and 2 and 3 somehow? Is there any way that we could get 30 from any combination of 3 and 5 and 5 and 2 and so forth? Yeah, exactly. So if we did 5 times 2, which is 10, times 3, that would make 30. So let's go ahead and combine the 5, 2, and the 3 together. That'd be 30. And then what would we have left over? We'd have the other 5 and the other 5, and then the other 2, right? So what is the remainder of 30 when you divide by 29? So how much is left over if you subtract 29 from 30? 1, right? So replace the 30 with the 1. And then you'll have to just 5 times 5 times 2, mod 29. Now, 5 times 5 is 25, which is less than 29. And 5 times 2 is 10, which is less than 29. So there's no way of reducing the rest of it. So the rest of it we just have to figure out the hard way. So what is 5 times 5 times 2? What is 5 times 5 times 2? 50, correct. So what is 50 mod 29? So to figure out 50 mod 29, just subtract 29 from 50 and see what's left. So what is 50 minus 29? It would equal what? 21, right? So the final remainder that's left after dividing 50 by 29 is just 21. So 1500 mod 29 is 21. Let's try doing one more thing with an exponent. So we practiced two problems with modular arithmetic when we're just dividing by a number and finding the remainder. Now let's do one where we have an exponent. So somebody give me a number between 10 to 20. 14. Perfect. Now somebody give me a number between, let's just say 30 to 40. 39. And then somebody give me a number between 5 to 10. 7. Okay, perfect. So we have 14 to the power of 39 mod 7. So once again, we're going to look at the power first because that's the most powerful part of it. 39. What's the biggest power of 2 that can go into 39? And remember, powers of 2s are things like 1, and then 1 times 2 is 2, and then 2 times 2 is 4. 4 times 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So what's the biggest power of 2 that can go into 39? 32, right? So 39 is 32 plus what's left out of 39 if you subtract 32 from what's left? 7, right? So 7 is left. What's the biggest power of 2 that can go into 7? 4. So what we're doing right now is we're expressing 39 as powers of 2, starting from the biggest first. Biggest first. You have to start from the biggest first. So 39 is 32, and then 32 leaves you with 7, and the biggest power of 2 that can go into 7 is 4. But what's 32 plus 4? 36. So how much is left now? We have 36 and you're trying to get to 39. You only have 3 left. So what's the biggest power of 2 that can go into 3? 2. And if you have 2 and you take away 3 from it, you only have 1 left. And the biggest power of 2 that can go into 3 is 1. So 39 breaks down into 32 plus 4 plus 2 plus 1. You have to express it as powers of 2 starting from the biggest to the smallest. Then what you're left with is you write 14 to the power, instead of saying 14 to the power of 39, you say 14 to the power of 32 plus 4 plus 2 plus 1, right? Mod 7. And then we separate the 14 to the 32 plus 4 plus 2 plus 1. We separate that using the rule of algebra into 14 to the 32 times 14 to the power of 4 times 14 to the power of 2 times 14 to the power of 1. Mod 7. Okay. Now, what is 14 mod 7? So we take the smallest one first. What's 14 mod 7? What? Yep, that's 0. So we get 0 to the power of 1 is still 0, right? And then what's 14? Now 14 squared is just 14 to the power of 1 squared. So 0 squared would be still the same. We get 0 to the power of 4. We get 0 to the power of 32. So what's 0 times 0 times 0? 0. And what's the remainder of 0 when you divide by 7? Still 0. So the answer to this whole problem is actually 0. So those numbers worked out nicely. So that's a good stopping point for us today. So does everybody remember that basically I took something 14 to the power of 39, which is like beyond the ability of your whole calculator to do. And then by expressing it as powers of 2, I reduced it down to a really small number like 0. And then we did the same thing on the last one. We reduced that one down to 1. So does anybody have any questions about that? All right, perfect. Well, I'll look forward to seeing you again next time. So we don't have any homework assigned for today. However, they'll be sure to be reading really, really carefully through chapter 4 and try to look at and think about all of the examples in chapter 4. And if you want to, you can even try to look at some of the homework questions on your own as well. So good job, everybody.